Spend your entire day carrying heavy wooden buckets of water uphill, then do it tomorrow, and the day after that, for your entire life, until the labor itself became the limiting factor. That was the daily operational reality on a muddy riverbank in Alexandria, 3rd century BC. You are looking at a problem measured in pure physical misery. 1 cubic meter of water weighs exactly 1 metric ton if your agricultural terraces sit 10 meters above the river basin. Forcing thousands of humans to haul that weight manually is a losing economic battle. The solution was not more workers. Ancient governments already had plenty of those. The problem was that the human body was a limited engine for moving massive amounts of material. If your entire civilization's food supply relies on an army of exhausted men breaking their backs to carry pottery jars day in and day out, your strategy is broken. The Nile was free. Transporting the Nile was expensive. This was exactly the kind of bottleneck that engineers like Archimedes targeted. They solved the problem the same way engineers still solve problems today, by making gravity do most of the heavy lifting. He documented and refined one of the earliest rotary water lifting machines in recorded history, the Archimedes Screw. Engineers love elegant solutions. Farmers love solutions that actually work. The Archimedes Screw managed to satisfy both groups. The machine had no valves, no pistons, no high-pressure chambers, and most importantly, no interest in being complicated. From the outside, it looks completely unimpressive, just a long, boring wooden cylinder hiding a central timber core. To build the internal helix, ancient carpenters likely used flexible wooden planks, sometimes softened through steaming or soaking before being bent around the core to form a continuous, tight helical blade. This assembly was then sealed within an outer casing of heavy wooden staves, pinned with wooden dowels and bound tightly by outer iron hoops. Similar in principle to a heavy wooden barrel. To start the machine, nobody needed a degree in advanced mathematics. You just place this heavy cylinder at a carefully chosen incline, often within a few tens of degrees from the horizontal, depending on the required lift and screw geometry. If the tilt is too steep, the water simply drains backward over the central core, rendering the machine useless. The angle must be precisely calibrated to the pitch of the internal helix, so the liquid can accumulate without spoiling the continuous spiral. Submerge the bottom end into the flowing river and begin turning the crank at the top. Every turn traps another pocket of water. Another turn moves it higher. Another turn repeats the process. The water is not sucked up the tube by a vacuum, atmospheric pressure, or mechanical suction. As the helical blade rotates, its submerged edge acts as a scoop, isolating a specific volume of water inside the lowest pocket of the screw, because the cylinder is tilted. Gravity forces that water to sit at the absolute lowest point of its local curve. As you keep turning the shaft, the physical geometry of the helix moves forward under the liquid, forcing the water pocket to climb upward along the rotating wooden track. The water is essentially walking up a continuous incline without ever changing its relative position inside the tube. The operator turning the crank is never lifting the crushing weight of the entire water column simultaneously. The geometric design allows a single human to divide and move isolated, lightweight compartments of liquid sequentially from one pocket to the next until it pours out at the top. This design completely bypassed the manufacturing limitations of the ancient world. In the 3rd century BC, making high-pressure piston pumps with reliable, airtight valves and precision leather seals was exceptionally difficult at a large commercial scale. A standard piston pump demands absolute structural perfection. One tiny air leak, the vacuum breaks, and the whole mechanism fails. The Archimedes screw simply did not care about being perfect. Even if the wood warped under the hot sun, expanded from moisture, or leaked slightly along the seams, it kept working. Minor leaks reduced efficiency. They did not destroy the machine's ability to function. It was a rugged, low-pressure system that happily swallowed muddy water, gravel, sand, and heavy river debris without jamming. The machine's greatest talent was not intelligence. It was stubbornness. It was a remarkably resilient machine for the ancient world, requiring far less precision manufacturing and maintenance than high-pressure pumps. Eventually, this simple wooden tube went from watering muddy cabbage fields to saving the largest superpower ship in the ancient world. King Hero II of Syracusia built the Syracusia, a massive luxury transport ship designed to carry thousands of tons of grain, defensive catapults, international dignitaries, and an entire cavalry unit complete with horses. A ship of this unprecedented size had a terrifying structural flaw. It constantly leaked seawater through its wooden seams, particularly at the keel where the water pressure is highest. If you cannot throw that water out fast enough, your expensive superpower asset becomes a permanent part of the ocean floor. Later accounts attribute a giant screw pump to Archimedes' solution for managing the bilge water aboard the Syracusia. The machine was angled down into the dark, filthy reservoir at the absolute bottom of the ship, drawing the dense, salty, trash-filled liquid directly from the floorboards. A sailor operating such a pump during a voyage would have faced a grueling task, turning the crank while the ship tossed and the bilge filled with stinking water. The operator never needed to understand the advanced geometry of the helix. His arm muscles simply bore the weight of the water, while the wood did the calculating. Turning that crank, the crew was able to eject large volumes of salty bilge water with far less labor than traditional bucket chains, giving the giant ship a highly reliable defense against progressive flooding. The invention of the screw pump was not a simple irrigation fix. It was a masterclass in making physics your servant. Instead of fighting the crushing weight of the entire river at once, early engineers trapped it in small, manageable pieces. They exploited gravity and geometry to move water upward with remarkable efficiency, proving that long before humanity understood fluid dynamics, we were already using mathematics to make water run uphill.